Hamming quasi-cyclic encryption. And here it talks about this is the new algorithm. It's based on different math than Kyber and is a backup system. It turns out to be easy to do in Python, easier than the other one. So here's security levels. These are the security levels for normal encryption, symmetric encryption before quantum, and the old public key systems too. You have less than 112 bits. Those are not considered safe anymore. 112 is acceptable, 128 is acceptable, 192 and 256. We should be getting away, and here's 2030 and 2031 and beyond, and they say 128 to 256 bits of security should be considered okay. And they call these levels 1, 2, 3, and 4 down here, the acceptable levels of encryption. But in post-quantum, they're trying to develop a new definition of levels, and these are sort of a provisional definition. And here's they are. Level 1 is as strong as AES 128. Level 2 is the hash. Level 3 is as strong as 192, and level 5 is as strong as AES 256. That's the idea. And so the HQC algorithm has 3 levels that are intended to meet those levels of security, 128, 192, and 256. Now, the actual key is a lot longer than that number of bits, but it provides a level of security that is considered to match that level of bits for like AES. So like you say, this smallest one is as good as AES 128, and the big one is as good as AES 256. As you can see, the key gets longer. So now this is a new system, so the libraries are not available in any simple way. You have to first build them from C code and then put the Python wrapper on them, but it turns out to work. And I wrote these instructions on a Debian 12 Linux machine. So you can do it that way, but I wondered if you could do it in the Colab environment, and it turns out you can, although I had to change a few things. And so if you're going to do it in Colab, this video, you should watch this video and follow it to see the little differences. So the first thing you have to do is you have to do sudo update and sudo install cmake. Then you have to clone the repository, which will get you the source code, and then use cmake to build it with a few cmake commands here. And this takes maybe 10 or 15 minutes in the Colab environment here. And the way you do these things is you put an exclamation point in front of each of those commands because they are bash shell commands. They are not Python commands. And that worked. As you see, it took some time, 93, 94%, but it finished after maybe 10 minutes, building the thing and installing it. I wondered if I would be able to do sudo, but it took it. So apparently you do have sudo privileges in your container in Google Colab. So I was glad to see that. All right, and then the next block of code is here, and this is the Python code. So if you go down here, I think I did this too, the virtual environment. Let me check. No, I didn't. I skipped that part. So that's what I would say, skip this part. If you're working in a Linux environment on your own virtual machine, you'll have to make a virtual Python environment here. They force you to do that on modern systems, but the Google Colab is not forcing me to do that. So I didn't do any of this. I just skipped this whole section and then go down here. Now here I do a git clone. Now there's a little bit of a problem here. When I tried to move into this directory and then install with a dot in that directory, somehow it didn't work. So in the Google Colab environment, it seems to forget what directory I'm in between one command and the next. So I had to modify this a little, and here's what I had to do. I do the git clone, I had to put it in one line. cd to the directory, then 2 ampersands, then pip install dot. That worked. Because if they're on the same line, then it does remember what directory it's in. If you put it on a separate line, it seems to forget. So that was the difference. Other than that, everything went through fine. And now I think everything went exactly as expected. You run a Python environment. Now, of course, you don't have to do this in Google Colab. You're already in a Python environment, but you just put in all the rest of this. So you import the library, which is OQS, Open Quantum Safe or something like that. You choose the algorithm, and we're going to do the lowest security version, HQC 128, just to make life easy. And so here's what you do. You may do a key encapsulation as client and another one as server. And since you're doing encapsulation, this is the equivalent of Diffie-Hellman key exchange. What the encapsulation algorithm is going to do is negotiate a shared secret between two entities. So we have a client and a server. We generate a key pair on the client, and then we create a shared secret here by calling the encap secret, and then make the shared secret client and secret key client. So this way I've created the secret key and the public key and the shared secret, which we would exchange using this algorithm with a Diffie-Hellman-like system. So then you can just print them out. I print how long they are, and I print just the first 20 hex characters of each one, since they're pretty long. And so that should be here. You'll see, run that. And so here it is. It installs something. It takes a few seconds, but there you go. It finishes. And so the public key is length of 2249, and the secret key is 2305. Remember those numbers, 2249 and 2305. If you go back here and look, that's what they should be, 2249 and 2305. That's the expected value for this version of the algorithm. So that's good. And here's the first 20 characters of it in hex. And here's the shared secret from the client side and the server side. And of course, the point is, those are the same. They can negotiate this shared secret while trading encrypted stuff that is not easily related to the shared secret, and deriving the shared secret from the stuff that was sent over the wire would involve solving the hard problem. So in that respect, the general structure is the same as RSA. So now that we have a shared secret, I just thought I'd finish the job. Once you have a shared secret, then it just does something we've done before. If you have a shared secret, then all you have to do is derive an AES key from it and encrypt your data with AES. So this is the code that does PBKDF2, password-based key derivation. And so I used SHA-256 and a 1024 rounds to take the shared secret and turn it into a 16-byte key. So if you run that, that'll create an AES key, and there it is, 16 bytes, random hexadecimal digits. And here I choose a message, and I made it a multiple of 16 characters so I don't have to worry about padding. And then I encrypted it with the version of AES that is recommended these days, which maybe I didn't need to worry about padding, but anyway, which is G-Galois counter mode is the recommended way. So I added an initialization vector and encrypt it using AES. So this plain text message turns into this hexadecimal blob of ciphertext, and you can decrypt it the same way, and you'll get back the original text. So, and then you can print details of the server. That's how you get a flag to show that you did this. So that's what I wanted to show you. It's very easy to implement with Python. Even though the underlying math is complex, you don't really have to worry about that. The Python library is pretty easy to use. All right, so that's what I wanted to show you about that one. Let me stop recording.